the new lecture. And in this lecture, I'll be covering first the review of what we had gone through in the last lecture, and that is if you can see that in the previous lecture we have covered the concept of degree of freedom, and then we specifically discuss about the degrees of freedom of a rigid body. Then we discuss the generalized coordinate concept of the generalized coordinate, why it is necessary, and the configuration space. So degree of freedom is like you need a minimum amount of, or minimum not amount, minimum number of the coordinates which you need to configure the system. Or degree of freedom gives you the idea of how many translational or rotational, or how many possibility of the motion of a object which you are considering. Then degree of freedom of rigid body, we discussed that that it's going to be 6 degree of freedom, and whatever the number of particle constituent particle of the rigid body, it's always going to be the 6 degree of freedom. But if the rigid body is pivoted or a pivot, then 3 degree of translation motion is like deleted from the 6 degree of freedom, and you just have the 3 rotational motion related to that rigid body. Then we discuss about the generalized coordinate. That was basically when you think about a system which is free and then you constrain the system, then what happened? The moment you constrain the system, the generalized the coordinates through which you configure or try to see the position or what is the configuration of the system, they are not independent, they got dependent to each other. So in order to uniquely define the configuration of the system, you need the coordinates which are completely independent, and that is the generalized coordinate. Those coordinates are the generalized coordinate. And because you see that, like in case of the pendulum, if you remember that in order to specify the position of the pendulum, if you need x and y coordinates in 2 dimensions, if you talk about, but if you, the moment you put a constant that the length of the pendulum is fixed, that is x square plus y square equal to L square. So x and y are now these 2 coordinates through which you are specifying the position of the bob of the pendulum. These are now no more independent, they are dependent. So now we need a coordinate through which we can specify the configuration of the pendulum or the position of the pendulum, during the oscillation where the position of the pendulum is. I need a coordinate which can specifically define this position, and that has to be independent. And if you remember that comes out to be theta. So if I say that this is my pendulum, then I either, if I can explain this the position x and y, but the moment I fix this L, it becomes dependent coordinate x and y. Now with this theta, which is my generalized coordinate, is now independent coordinate through which, if I know the theta, the moment I know the theta, I know where this pendulum is going to be. Okay. And then we discuss about the configuration space. So that space is basically spanned by these generalized coordinate. So configuration space is basically the space spanned by generalized coordinate. Generalized coordinates. So if you remember, like in my physical space, for this case of pendulum, this pendulum, like if I extend it, this pendulum can oscillate from this position to this position, and we can have, depending upon the x-axis and y-axis, I can define that whether this is here, what is x1, x2, x3, what are these, like x1, y1, x2, y2, x3, y3, and so on. We can define in terms of x and y in physical space. So in physical space is generally it is going to be the position of this is going to be on the x and y space, and between this point and this point. But in the configuration space, in which the generalized coordinate is that my theta. So in the configuration space, this is going to be a straight line with theta, and this is going to be mean position, where the angle, this angle the mean position is going to be 0, and then at this, like this is pi by 4 when you go to this position, and then when you go to this position this become pi by 2, and similarly from here it comes back, and here mean position then goes to minus pi by 4, and then goes to this position, that is minus pi by 2. So you see in configuration space, this is my which is spanned by the generalized coordinate theta, and this is my physical space which is spanned by the coordinate nx, y. So now these things we had discussed already in our last class, and then we will move forward to discuss the generalized velocity. So as we have a coordinate, if we differentiate it, we're going to have the velocity. So if my coordinate is a generalized coordinate, and then if I differentiate it, this is going to be the generalized velocity. Okay. So for how you define the generalized coordinate mathematically, that if I have some system in physical space whose coordinates are my Ri, and then they are, if I put the constant, and that means if you remember, if I have k number of constant there, so then the degrees of freedom are reduced by 3n minus k. So because where 3 is the dimension, which dimension we're talking about, and then s is the number of particle, and k is the number of constant. So the final degree of freedom goes to 3n minus k. So when you constant the system, the degree of freedom reduced from as a free particle to constant particle. So if I have a system consisting of n number of particles, say n number of particles, then I can define a generalized coordinate which are completely independent, and that could, it's n generalized coordinate. This is q1, q2, q3, qj. That is, I have q1, q2, q3, and I have qn number of generalized coordinate. Then what is, and the second important thing was that when we go from a physical space to the configuration space, these are interconvertible, because when I have x and y space to generalized coordinate space theta, where I have constant the r is fixed. Okay, if you remember, then this is my generalized coordinate, which is 1, and this is in physical space. So if I write x now depends upon r and theta, that is going to be r is fixed. So say r is fixed, say r is constant, so this is some a cos theta, and this is y theta, this is going to be a sin theta. So the coordinates over which the constraints have been applied, and then in order to we have specify the system uniquely, we define the generalized coordinates. Okay, q1, q2, q3, so on. So if I differentiate it, that if I'm going to have the velocity, that is del dr by, this is dr by dt, and because r depending upon this q, okay, so r partial differentiation of r with respect to q, okay, and it probably depends upon time t. Then because I'm differentiating with respect to t, so r depending upon first q and then t, so r with respect to q, and then q with respect to t, and then r with respect to t. Okay, so that means this is this quantity, if you remember this quantity delta r q k by delta t with respect to t, that I'm going to represent with q dot. Anything which is with respect to time, differentiated with respect to time, now in the Lagrangian formalism it is represented as with q dot. Okay, and then this delta r upon delta q is there, and this with respect to delta t. Fine. So I think you understand why I have written this, because if you suppose this, if I have something some function say x and t, okay, function x and t, if I write x and y, see if I write df by dt, okay, df by dt, that means I'm supposing that this x is depending upon what is this x is what is x depending on, and then I have to have this t, okay, delta x by delta t, and this x is depending upon y, so then I will with respect to r, and then what I do delta r by delta t. Okay, so first r x is depending upon r and r is depending upon t. Similarly I have to have, because y depending upon r, and then say So this is going to be r, and this is delta r by delta t. Okay, so this is r is not some r which depends upon x and y. This is not. So r is some variable here I have chosen. So like could be any other variable, not the position vector here in this case. Okay, so that's why, because r depends upon q and q can be time dependent also. So then we have written like this. So when I differentiate this, this is the velocity. I have this delta r upon delta ri upon delta qj is aij and q dot k, and this delta r by delta tt. Okay, so if my constants are not depending upon time explicitly, if the constants are holonomic and scleronomic, basically not depending, being holonomic because we are normally going to treat in this the holonomic constant, which we can be specified in terms of a simple relation f1 r1 r2 r3 and so on. Time is going to be some simple equation. So if it is not so this is going to be 0 in this case if time dependency doesn't occur explicitly. So what we have is v is here is aij this times q dot k. So because qk is my generalized coordinate, and this, if this is, and q dot k is my generalized velocity. Okay, so and this is going to be the matrix. So if I, so how I'm going to get this q dot k, if I do the matrix calculation, so I can get this q dot k from this vi. So for example, if I have a particle position in Cartesian coordinate, if you remember that, I can represent x to r cos theta and y to r sin theta and its component. So like, let's try to do the same thing. When I have r, and let's differentiate it. When I have x, let's differentiate it. This is x dot. Okay, so this is nothing but dx by dt, as we did here, dri by dt. So this becomes, because r is a variable here, r can change. Okay, so what we are talking about is I have a free particle. Okay, this is like moving, and this position of this is r and this is theta. So it can, like, it is moving like somewhere like this. So I can have r, this is here, and if this is the position of this particle, this r can change and theta can change and so on. So that's why r here is not constant, r here is a variable. So first we this is r dot, and then I have cos theta, and then this is r is kept constant, and then I have cos theta is my sin theta with minus and then theta dot. Okay, similarly we differentiate y. So this is r dot sin theta, first function, differentiation of the second function, and plus second function and differentiation of the first function. So this is now, r is now kept constant, and then if I do this, this is d dt of sin theta is basically delta sin theta by delta theta and delta theta by delta t. So this delta theta by delta t is my theta dot, and this delta sin theta by theta is my cos theta. Okay, so now you know that this is my x dot and y dot in place of vi. So now we write the magnitude in terms of this. When you have the velocity, the complete velocity is x dot square plus y dot square, and this if you remember, this x dot is r dot cos theta, x dot is r dot cos theta minus r theta sin theta, r theta dot sin theta, and you have y dot is r dot sin theta plus r theta dot cos theta. So if you square this and add this, you're going to get r dot square and r theta dot square, r theta ka whole square, r square theta dot square. So in polar coordinates we have r theta, the generalized as a generalized coordinate. So corresponding generalized velocities are for this, because in polar coordinate my q1 is r and q2 is theta. These are my generalized coordinate, and this q1 dot is my r dot and q2 dot is my theta dot. These are my generalized velocity. So in normal conditions, what you have in physical space, the velocity is x dot square plus y dot square, that is vx this is Vx and this is Vy, and now in generalized terms of generalized coordinate, the generalized velocity of r theta and theta dot. But if you constrain the system that when the moment if you constrain the particle, if you constrain the particle that you don't have, you cannot go somewhere else, you cannot go like this, that you have to have along this radius r. Okay, you cannot go, you cannot trace this path, you cannot trace this path, you have to have along this radius. So this, you fix this r, and theta can vary from this to this. So the moment you fix r, so this r dot, this generalized velocity is going to be 0 and corresponding to the r generalized coordinate, and then we are only left with one independent coordinate and the corresponding generalized velocity. Okay. So for the particle constant to move on the space of surface of the sphere, r is constant. If we sphere की बात करें, तो sphere में you have generalized coordinate q1 equal to r, q2 equal to theta, and q3 equal to phi. There are 3 generalized coordinate, and the corresponding generalized velocity are r, theta dot, and phi dot. These are q1 dot, q2 dot, and q3 dot. So if the moment you constrain the system, so particle has to move on the surface of the earth, so this is going to be 0. So I just have the generalized velocity as theta dot and phi dot. Okay, fine. Now let's move to after this concept of generalized velocity, this is important concept of virtual displacement. Okay, so what do you mean by the virtual displacement? In the first thing you should know that why I am telling is virtual, because when we talk about the term virtual, that means the time is involved in this. So displacement, we know that if you apply a force, on certain object, like this is my object, this is some block, if I apply a force on this, so this is going to be displaced to certain distance. Okay, so this is my ds, this displacement. I'm applying a force, this is moving at distance ds and in some time dt. But it may happen that the concept of virtual displacement is this: if I am applying the force on this object, what is happening, that there is an infinitesimal displacement of the object is taking place. That is, this is going to be delta s at any instant. So that means delta t is 0 in this case. That means at that instant, when I am applying the force at that particular moment, there may imaginary displacement take place, that is known as the virtual displacement. Like it is hard to imagine, but like the concept of this, that's why it is known as, so that is not a real displacement. But real displacement always involves the time, but the virtual concept of virtual displacement, delta time involvement is 0. How much small amount of time, there is no 0, there is 0, but the displacement is the infinitesimal displacement we can think of. Like for example, like if I'm applying a force on this, if I'm applying the force on this, so I'm applying the force, and for that instant when I'm applying the force, there is a possibility that there is a deformation in this. Like for example, if you apply a force on this, if I have a surface kind of this, if I apply a force on this surface, there is a possibility that this surface is going to be like this. If I apply force from this direction, this is going to be like this. Okay, so not in case of the virtual. Real displacement may, that I can deform the body or I can displace the body. But in the virtual displacement concept, like the moment I am pulling it, there is possibility there is an imaginary kind of like a displacement is taking place without involvement of the time. So the displacement is called virtual to distinguish from the actual displacement occurring in a time interval dt. So I'm not going to involve the time. So this is the concept of virtual. This is how you think that what do you mean by saying the virtual displacement. For example, if you consider your pendulum, that is this pendulum with mass m. So if I consider that now the position of this pendulum is can be represented by, because this x and y components. So if you see this length is L, okay, this is delta theta. So this is angle theta, so this is going to be, this side is going to be L cos theta, and this side is going to be L sin theta, okay, because, and this particular, so I'm not bothering about this part right now. So the position of this x is like, this is my x-axis, this is my x-axis, along this is my x-axis. So this part is x component and this part is y component. So with this L sin theta with x direction, and this is my cos theta, L cos theta with j direction, but j is here, is the negative sign is here. If you remember, this is negative sign. Why? Because y is like starting from this, so this is plus y, and from here negative, this is minus y. Okay, so I am below this line, below this reference point, so that's why it says minus j. Okay, so this is going to be plus j from there, and this is going to be minus j if this is my reference x-axis. Okay, so this is my position vector r with respect to x and y. Now if you suppose that there is a very small displacement, very small angular displacement, this is say delta theta. Okay, this is some imaginary, you apply certain force and some imaginary delta t is there. So if I differentiate is delta r, what is delta r? So because r depends upon theta, so delta r by delta theta, and this delta theta is the real displacement. So what is this delta r by delta theta? I can figure out from here, because this is L is fixed, so this is cos theta I, and this is, because this is sin theta, so sin theta becomes my cos theta, and then this is cos theta becomes minus sin theta, and minus becomes plus, this is plus sin theta and delta theta. So here delta theta is the virtual angle, a small image rotation. Okay, this is what the change in configuration of the system at the particular instant. And for example, bead, the second example is a bead on a fixed wire. So if like a bead can move only along this wire, the bead has to be along this wire only. If the bead cannot go like this side, bead cannot go like this side. Why? Because the delta r must be along the wire, since the displacement of the wire violates the constant, because the bead has to be along the wire. If it is not along the wire, the constant, that is this is constant, that is y equal to x tan theta, the constant will not remain there for the motion of the bead. Because of this, we have certain generalized velocity and coordinate. Okay, next, moving further, so in terms of the generalized coordinate, how you define the virtual displacement is like, we define the generalized coordinate like this. This is Ri, and this is Q1, Q2, Q1. We have the generalized coordinate. If we want to, in real displacement, because it is time dependent also, if I want to find from delta Ri to this Ri to delta Ri, so this R depends upon Q and then delta Qk. Okay, k going 1 to n number of particles is there. Okay, and then it depends upon time also, so I have delta R upon delta t, and this is delta t. This is exactly how you define this total differential. Okay, so this, if you remember, but for virtual displacement also, delta t is not there, delta t is 0. So when you're talking about the virtual displacement, there is no involvement of time, so only this remains live. So this delta Ri is delta Ri upon delta Qk. This is my virtual displacement, definition of the virtual displacement in terms of the generalized coordinates. It is basically, it is a mathematical tool which is used to test the equilibrium of the motion of the system. This is very important. So why we are defining the virtual displacement concept, so without actually disturbing it. Okay, so we'll talk later on that what do you mean by equilibrium condition without actually disturbing the system, without actually deforming the system. So a virtual displacement is a opposite infinitesimal, is a possible infinitesimal change in configuration of the system consistent with the constant imagined to occur at a fixed instant, not delta t. Fixed instant means delta t is going to be 0. Fine. Now, why we need to define this concept of the virtual displacement? Okay. So one, I told you that there is going to help out to find out the equilibrium position of the system. So the first answer to this, that why we need to define it, is to apply the principle of virtual work. Okay, and this is another very important concept which actually help out to solve the many dynamical problem or mechanical system which are under constraint. So what is the principle of virtual work? We will go on with this, but you see that Newton's law deal with real motion, this we know, but in constraint system, like this is a constant system, pendulum is a constant system. So what you do, pendulum hai, you do up you displace the system and release it, and it is oscillating like this. But we don't actually bother like what kind of forces are acting on the dynamics of the system while the system is moving. So there we have we bother about this weight of this ball, and there is a tension also in this while it is motion, and tension along the string of this. Similarly, if the bead is moving along a wire, fixed wire, so you have this is the weight, the mg force is acting, and there this normal force is acting along this perpendicular to this bead. So these kind of forces, like bead on a wire or simple pendulum, so normal forces, tensions, and different alag force like friction forces acting. So to keep the motion, if these forces are not there, so the motion is not possible. So, but we don't always know these forces. There are conditions, there are complicated system or mechanical system where we don't know that what are the forces, other forces which are coming into play when your mechanical system is in motion. So to avoid dealing with those kind of forces directly, we use the concept of the principle of virtual work. Okay, so and when you're talking about the work, there has to be displacement. When you're talking about the virtual work, there has to be virtual displacement. So concept of virtual displacement is introduced to define the principle of virtual work, and principle of virtual work is the concept is introduced to actually get rid of all those forces which we basically we don't want to we don't want to complicate our system. So this virtual work and virtual displacement help to express this without involving unknown constraint forces. Okay, so this is like tension in this simple pendulum is one of the constraint force. Normal acting on this bead is also a type of a constraint force. So because we will try to show that the work done by this this virtual displacement is going to be 0. There is no constant forces do no virtual work. Okay, so because there's the virtual displacement is there, but the virtual work is not there because of the constant forces. To define the principle of virtual work, so before that we need to know two equilibrium, what is static equilibrium and what is the dynamic equilibrium. Okay, so so first we know that dynamic equilibrium is basically when there is no forces acting, overall net force or effective force is 0 on a system, then this system is in equilibrium, and that correspond to no acceleration of the system. Okay, that is in general we talk about equilibrium in mechanical system. So we have, for equilibrium, we have a static equilibrium as well as the dynamic equilibrium. So a body is said to be in a static equilibrium if it is at rest, that there is no acceleration, and it remains as rest until all action of all forces are 0. So all effective forces are 0, or when you talk about the rotation or torque are 0, then there is, if you see overall, there is no velocity, so there is no acceleration. For example, if a book is on the table, if you see this book is on the table, So what kind of forces are acting? One force, that is the weight of the book, and then the earth is attracting this book, and from the Newton third law, the earth is this book is also attracting this earth towards itself, so they are equal. And one is the normal force which is acting from the table to the surface to the book, and then corresponding reaction force, okay, is acting on the surface. The total force is basically not able to move the book, because the book is at rest, okay, because the book is at rest. So that's why the velocity is zero. The force is acting on the system, this normal forces are acting on the system, this gravity is acting on the system, but the situation is such that in spite of the forces that are acting, the total effective force and the torque is zero, and then the velocity is zero. So that is known as the static equilibrium. The system is completely at rest, okay. This is what you mean by the static equilibrium. The so I think in the next lecture we will try to uh, talk more about the dynamic equilibrium, and then we will move to what is the principle of virtual work, which is very important concept to build up the Lagrangian formulas. Okay, thank you very much.